All right, let's talk about a part of math that gets a bit of a weird reputation, complex numbers. But here's the thing, we're not going to treat them like some strange invention. Instead, think of this as a journey of discovery. We're going to build them from the ground up, and you'll see they're not just some wacky idea, they're actually inevitable. So let's get started.
You know the number line, right? We've used it forever. It's flat, one-dimensional, simple. But what if we wanted more? What if we tried to build a number system that wasn't just a line but a whole two-dimensional plane? What would that even look like? How would the rules work? Well, that's our mission today, to see if we can construct a true 2D number system completely from scratch.
Okay, so first step, we need a map. We need a landscape for these new numbers, and that's the complex plane. It's actually super simple. We just take our good old number line and lay it down flat. That's our horizontal, or real, axis. Then we draw another line straight through the zero, but this one goes vertically. We'll call that the imaginary axis. And just like that, any point on this grid, any location you can possibly point to, is what we're going to call a complex number. So how do we give these points an address? We use this little formula. Z equals A plus BI. The A is just your regular number, telling you how far to move left or right on the real axis. The B tells you how far to move up or down on the imaginary axis. And then there's that little I. The only thing we need to know for now is its one single fundamental rule. I squared equals -1. I know, it sounds totally bizarre. Just trust me on this for a minute, because we're about to see what that really means.
So we have our numbers, we have our plane, now we have to figure out how to actually do stuff with them. What does it mean to add or multiply in this new 2D world? Let's start with the easy one, addition.
Turns out, adding complex numbers is a piece of cake. It's exactly like adding vectors, if you've ever done that. You just add the real parts together, and then you add the imaginary parts together. Visually, it's like just shifting a point across the plane. Nice, simple, and predictable.
Okay, addition was no big deal, but multiplication, oh, this is where things get really interesting. This is the real puzzle. How do you define multiplication in a way that makes sense? Not on a line, but across an entire two-dimensional surface. This is where the magic is.
To crack the 2D puzzle, let's actually go back to the 1D line for a second. What does multiplication do geometrically? Well, if you multiply by 2, you stretch everything. You push every number twice as far away from 0. But what about multiplying by -1? That doesn't stretch anything. It flips everything. It's a 180-degree rotation around 0. So you see, even in 1D, multiplication already does two very different things. It stretches and it rotates.
And that right there is the big question. That's the challenge. We need to come up with one single rule for multiplication that can handle both stretching and rotating, and do it consistently for every single point on our entire 2D map. How on earth do we do that?
And this is it. This is the moment where that weird little rule from the beginning, the I squared equals -1 thing, suddenly stops being weird and reveals its true, beautiful geometric purpose. Okay, so we just saw that a 180-degree rotation is the same as multiplying by -1. So what about a 90-degree rotation? A quarter turn? We don't really have a number for that, or do we? What if we just define one? Let's just create a new operator, a command that means rotate 90 degrees counterclockwise. And let's give that command a name. We'll call it I.
Let's just walk through this logically. Start at the number 1. Okay? Now apply our new operator, multiply by I. That rotates us 90 degrees, and we land straight up on the imaginary axis, at the point we call I. Simple enough. Now, let's do it again. From where we are, let's multiply by I a second time. Another 90-degree rotation. Where does that put us? We've gone 180 degrees in total, and we land at -1.
And boom, there it is, the big reveal. Applying our 90-degree rotation I 2 times in a row is the exact same thing as performing one 180-degree rotation. And we already know a 180-degree rotation is just multiplying by -1. So multiplying by I twice, or I squared, has to be equal to -1. It's not a weird rule somebody made up. It's the only possible outcome if you want rotation to make sense in 2 dimensions.
So we really need to stop thinking of I as an imaginary number. It's not imaginary at all. It's an action. It's an operator. It's the fundamental command for make a quarter turn on the plane. It's as real and essential to 2D geometry as the idea of backwards is to the 1D number line.
Okay, so we've built the system and it seems to work. But maybe you're thinking, is this the only way to do it?
Or just one of many? Well, the answer to that is what makes all of this so incredibly profound.
Now here's the part that just might blow your mind. This system that we just built up from simple logic, it's not just a solution. It turns out it's the only solution. Mathematicians have proven that this is the one and only way to make a two-dimensional number system that still follows all the basic rules of algebra that we rely on. Which means we didn't invent complex numbers, we discovered them. They were just waiting there, the one true way to do arithmetic in 2 dimensions.
You can think of any complex number as having 2 different personalities. There's the Cartesian form, a plus bi. That's perfect when you're just adding and subtracting, shifting points around the grid. But then there's the polar form, which uses the distance from the center and the angle. And that form is absolutely perfect for multiplication and division, because it's literally described in terms of stretching and rotating.
And the ultimate expression of this whole idea has to be Euler's formula. It's just gorgeous. It's this super compact way of saying that exponentiation with an imaginary number is rotation. This one little equation is the engine behind huge areas of modern physics and engineering, because it's the perfect language for anything that spins, turns, or oscillates.
And this is not just some abstract playground for mathematicians. This system is what makes modern life possible. It's the language behind electrical engineering, signal processing, even quantum mechanics. And it can create incredible beauty too. You've seen the Mandelbrot set, right? That infinitely complex fractal? The whole thing is generated by taking a complex number, squaring it, and adding another one, over and over again. That's it. All that complexity from one simple 2D rule.
So we started with a simple line, and we took a leap of faith into a second dimension. And what we found there wasn't just a clever trick, it was a fundamental, unique, and powerful mathematical structure that was just waiting to be found. It leaves you with this really fascinating question, doesn't it? If this is the inevitable math of 2D, what happens in 3 dimensions, or 4? What other amazing mathematical worlds are still out there, just waiting for us to discover them?